Building with textiles is a tradition which goes back thousands of years, from yurts made out of animal skins through to the Roman shade structures installed at the Colosseum. But the inclusion of technical fabrics within mainstream architecture has a more recent history. In the 1960s, German architect Frei Otto pushed the boundaries of membrane technology and opened people's eyes to what can be created with tensile fabric. 20 years later, ArchitenLandrell was founded with the aim of building technically advanced and aesthetically beautiful fabric architecture.
Since I started this company, and it feels like only a few weeks ago, but in fact it's almost 30 years, since those first years, much has changed. Fabric technology has advanced, design and engineering has become computerized, manufacturing techniques have improved vastly. But our original philosophy has remained the same. Few methods of construction can compete with the impression given by lightweight tensile structures. They bring style, curvature, translucency, and clear, large spans to building schemes. We have always thrived on working with architects and designers who feel as passionately as we do about fabric architecture. This presentation is designed to inform, inspire, and get people talking about the possibilities of working with tensile fabric.
The materials of tensile architecture. The materials used to create tensile architecture are constantly in development. As sustainability and performance issues become more and more important, we demand more and more from the technical fabrics we use. The biologically based woven cotton and canvas materials which were used to create the first fabric structures have been replaced by some of the world's most technical man-made fabrics to achieve lasting, permanent fabric architecture. Modern coated fabrics have similar aesthetic properties, but offer significant performance advantages such as increased strength, ease of cleaning, printability, solar shading, and acoustic characteristics. Modern coated fabrics will also resist the absorption of atmospheric moisture, resulting in much longer lifespans and better dimensional stability. In general, we use two generic types of fabrics: structural coated fabrics and mesh fabrics. Structural coated fabrics consist of a woven base cloth made of warp threads that run the length of the roll and fill threads across the width. This base cloth is then covered by a protective layer on both sides. Coated fabrics can be characterized by the fact that the woven or knitted base cloth provides the structural strength of the fabric, and the coating provides weatherproofing, color, and the required technical characteristics such as UV resistance, flame retardancy, and the welding ability. In contrast, mesh fabrics are made up of coated cloth with spacing between the thread bundles. With some meshes, the threads are coated before weaving. Due to the openness factor of meshes, they are primarily used as shading or light diffusing fabrics, but some laminated meshes are available which provide a weatherproof finish with a high level of light transmission. For external use, the coated fabrics most commonly used are PVC-coated polyester, PTFE-coated glass cloth, and silicone-coated glass cloth. They all offer differing properties for strength, durability, translucency, and of course cost. By comparing these with the client's requirements, we can help decide the optimum material for any project. PVC-coated polyester scores well when measured in terms of its strength. It is easy to dismantle and print on, is relatively cost-effective, and requires moderate maintenance. However, it doesn't last as long and has a lower light transmission than other available fabrics. In contrast, PTFE-coated glass cloth offers durability, strength, and Class O flame retardancy. However, it is not suitable for demountable structures and is one of the more expensive fabrics we offer. PTFE-coated glass cloth is often used in harsh climates, such as desert environments, due to its ability to withstand high levels of UV and sand abrasion. For projects where light transmission is important, silicone-coated glass cloth is a viable option. Offering many of the same properties as PTFE-coated glass cloth, silicone has the added advantage of requiring little maintenance and offering high translucency.
Architectural fabrics are going to be changing quite a lot in the future. We're already seeing advances in photovoltaics integrated with fabrics. We're looking forward to better recycling, better cleaning properties, better thermal properties, higher specifications on acoustics, also integration of lighting into tensile fabric.
The forms of tensile architecture. While it is possible to have a flat tensile membrane, the key to strength and stability in tensile architecture lies in the principles of double curvature.
Anticlastic curvature is where the curvature is in different directions or at 90 degrees to each other. When you lock the fabric into an anticlastic curve, as would be seen on traditional shaped tensile structures, you then have a very efficient use of a very thin membrane material that can only carry load in tension. Synclastic is if you have a convex or a concave surface when the curvature in the material is from the same direction.
Tensile membranes can create the most complex dynamic and fluid of shapes. However, the basics lie in 4 geometric forms: the hyperbolic paraboloid or hyper, the conic, the barrel vault, and the inflatable. The hyper is the traditional sail-like form which is often seen as synonymous with tensile architecture. A true hyper is a quadrilateral tensioned at 4 points, too high and too low, to create opposing curves. The theory of the hyper is often applied to other polygonal shapes, and complex undulating forms can be realized with multiple high and low connection points. The conic or umbrella form also adopts double curvature to give it strength. In this case, the loads are spread horizontally around the full fabric form and vertically from the apex to the base. Although featuring double curvature, in much the same way as the previous forms, the barrel vault can only be created with an inner steel, aluminium or timber structure tensioning the membrane in place to create the curves. In the case of all 3 of these shapes, the opposing anticlastic curvature allows the fabric membrane to withstand downward loads caused by wind pressure or snowfall, and the uplift caused by wind suction. At any point on the surface of an anticlastic curved membrane, the 2 different directions of weave are carrying the different types of load. The final form is the inflatable cushion, which adopts a synclastic rather than anticlastic form to create a dimensionally stable shape. Much like a balloon, inflatable cushions are created where constant air pressures form the fabric into a shape. Air pressure maintains the tension under which the fabric needs to be to absorb the environmental loads which will be acting on the membrane, trying to de-stress or collapse the shape. This cushion form is most commonly used with a clear foil material called ETFE foil, but can also be used with more traditional tensile fabrics such as PVC-coated polyester or PTFE-coated glass cloth. The uses and benefits of fabric architecture. Making a statement. It's undeniable that a well-designed fabric structure can make a big statement. The construction of London's Millennium Dome, Denver International Airport, and Ashford Designer Outlet all include iconic tensile fabric structures for exactly this purpose.
The fabric is incredibly useful within building design because it lets you bring bespoke dynamic shapes to an otherwise rudimentary structure. It also provides a good plateau for brand image and branding, as well as a focal point.
The entrance canopy at the venue in Bristol is a great example of how a tensile fabric structure can be practical whilst creating an eye-catching centerpiece, conveying a corporate identity, and transforming an otherwise regular building into something a little more special. Its size and depth provide coverage for cinema goers and passers-by to shelter from the inclement British weather. But in addition, note how the sculptural eye-catching form and colour-changing lighting make it stand out against the other boxy buildings. Whether it's an entrance canopy, an artistic sculpture, or a piece of point-of-sale material, the principle is the same. Tensile fabric structures allow creativity and practicality. Solar control. Curtains and blinds are the traditional ways of using fabric to control light transmission, but they are not the most exciting or the most creative. As architects look for more interesting ways to introduce light into a space, we look for ways in which that light transmission can be controlled, diffused, and reflected. Light reflectors and diffusers can direct sunlight deeper into a building, replacing or supplementing daytime energy. Combining a practical application with an aesthetic element is a key benefit of using tensile fabrics. Take this structure at the BBC offices for an example. These lampshade-style structures are formed using a lightweight framework and stretch fabric. They diffuse the direct sunlight and provide soft illumination for the space below. When the sun goes down, the same fabric structures can achieve startling results with uplights or backlighting. And in addition to this functionality, the aligned forms are a visual feature in themselves. Temporary installations. While fabric structures can last over 30 years, some fabrics lend themselves particularly well to being mounted and demounted again and again. Fabrics which are suitable for this application are used for everything from small exhibition canopies to the large-scale temporary installations erected for the London 2012 Olympics.
Well, I think the fabric structures are great for temporary use because they are very quick to install and deinstall. The equipment to do that sort of work is not particularly complicated or onerous.
Some fabrics lend themselves particularly well to temporary use. However, if it's constantly going up and down and being stored, then we have to think about the design in a different way. The fabric panels are smaller to ease storage and ease installation, and often the foundations or the way that we deal with the loads has to be changed.
This canopy, constructed every year for the Holland Park Opera season, is designed to be dismantled at the end of the summer and stored through the winter. As a result, the weight, size and number of steel columns supporting the structure were minimized. Much of the support comes from tie-down cables. The fabric is a flexible PVC-coated polyester, made up of panels limited in size to allow for easy handling and storage. In this case, the structure is designed to impose no loads on the existing buildings, so all ballast comes from permanent foundations. For tensile fabric structures which are relocated time and time again, or where foundations are not viable, ground anchors and water or sand ballast can also be used. Fabric architecture is particularly suited to many commercial and leisure schemes where a project life of 20 or 30 years suits the overall life of the project before it becomes outdated and needs redevelopment. The practicalities of fabric architecture. Acoustics. The introduction of fabric will offer qualitative acoustic improvements into any space that has lots of hard reflective surfaces. But acoustic meshes are now available that have been specifically engineered to absorb sound waves and reduce acoustic reverberation. These fabrics can be used in suspended structures such as kites or rafts, as tension screens or as wall and ceiling linings, and if drastic acoustic improvements are required, additional acoustic quilting can be added behind the fabric. Insulation. Fabric structures are not known for inherent insulation. A single layer of any of the technical fabrics we use will cover unheated spaces effectively, but offer no further insulating properties. However, by using multi-layer membrane systems, it is possible to improve thermal performance and even meet Part L building requirements. Multi-layer systems generally comprise of a thermal multifoil layer sandwiched between inner and outer tensile membranes. This gives the required U value but has the drawback of rendering the membrane entirely opaque. More recently, products such as nanogel have been introduced into the market which allow some light transmission to be retained but can be prohibitively expensive. Alternatively, good levels of insulation can also be achieved by creating an air-inflated cushion where additional layers of membrane trap pockets of air, which can result in U values as good as 1.18. Printing. Tensile fabrics offer clients the ability to print on their structure, which is something that traditional building methods do not.
Printing within the tensile fabric industry is a relatively easy way to bring some personal identity or brand into the structure itself. Being a fabric structure, printing is relatively easy when compared with solid or conventional buildings. It gives the artist and the architect free rein over how their structure will look, and equally as it is fabric, it can also be changed at a later date.
When looking at printing on fabrics, consider the colour and size of the image, how it is being lit. Is the print being used internally or externally? Do you need to see through the print? Will the print be used for multiple events? And is there a specific fire rating requirement? Lighting.
Lighting is a little bit different to printing. It gives you an organic and dynamic installation. It lets you change at will the look and the feel of the building to suit the situation, the time of day, the time of year. A good example of this would be for the O2 Dome, where for one night only, Prince was playing, his favourite colour being purple. At an instant, we can change the entire structure to be purple.
Environmental. As most of the fabrics and components we use can now be reused or recycled, the environmental impact of a fabric structure is far smaller than some less efficient traditional building techniques. PVC, silicon and PTFE can all be recycled and made into second-generation products. Tensile fabric structures also lend themselves to relocation. For example, when the inverted conic structures installed at the Millennium Dome were no longer required by the client, instead of dismantling the structures, we relocated them to Piarco Airport in Trinidad. The process of fabric architecture. Design. Every structure goes through its own design journey, whether it starts from a simple sketch or a more detailed architectural outline scheme. All structures require extensive design detailing to turn them into a final working plan. Designing a tensile structure is an art as much as it is a science. Throughout the preliminary design process, decisions are made on how the canopy will be constructed to meet the aesthetic, functional and engineering requirements set out by the project team. Decisions made at this point will affect the fabrication and installation methods. Boundary detailing is an essential element, falling into three main categories: curved or scalloped edges, straight edges, and fabric edges. A curved or scalloped edge generally consists of a cable enclosed in a pocket in the edge of the fabric membrane. The cables are held and tensioned at the corners by the membrane plates. In larger canopies, webbing belts are added parallel to the pocketed edge for reinforcement, but smaller structures may need no cable at all. As an alternative, it is possible to have an external cable connected to the edge of the membrane by a series of stainless steel link plates. Fabric under tension does not naturally form a straight line, so when a straight edge is required, the membrane is manufactured with a CADA or beaded edge, formed by sealing a flexible rod in a small pocket. This can then be trapped behind an aluminium clamp plate, bolted directly onto the structural steelwork, or slid into an aluminium luff track extrusion. A fabric edge can also be curved and fixed with clamp plates or luff track. Such edges normally require flashings or cover plates to ensure the edge is waterproof. Engineering.
The function of any shelter, any structure, is to stop nature impinging on your environment. Environmental loads, wind loads, suction, pressure, snow loads, snowdrift, they attack the fabric and the fabric withstands it. However, unlike traditional construction, they deflect to a degree more than a solid house. So there is movement, and it's through the movement and the small stretching and the stressing of the fabric that the fabrics will withstand those environmental loads. They're designed to do that.
The strength of a fabric structure and its ability to resist loads comes predominantly from the tension at which the fabric is maintained at.
Because of the nature of tensile structures, they have to be heavily engineered. I can provide picturesque designs, very flowing designs, very attractive to the architect, to the client, but I also have to make it work. There's a very large load in this fabric skin that is going to be transferred somewhere, whether it's contained within the structure itself or whether it goes back to the ground, whether it goes back to the surrounding building. If we don't put enough tension in the fabric and the wind picks up, then what you can get is a massive distortion of the fabric. And by distorting the fabric, that will increase a load back into wherever it's going. But also, the wind blows over the top, the canopy will actually lift. And what will happen with a strong wind is if the fabric isn't tensioned correctly, it'll flutter. That's why there's such high loads going back to the ground level or back to the frame or back to the building.
Canopies can contain their tensile loads within their own structural framework, transferring the load into concrete foundations or ground anchors. Or they can transfer their loads onto an existing structure. However, the large lateral loads often require the structure to be reinforced. As part of the preliminary design process, a load analysis is derived from a computer-generated form-finding model. This provides the typical load size and direction. Then, incorporating a factor of safety, an engineer will determine the design of the supporting structure, the size of the foundations, the required material strength, and the necessary tension. The boundary details are then engineered to maintain the tension and accommodate the movement that may be generated at the canopy extremities. In many situations, consideration for the load that snow will impose on a structure is equally as important as considering its ability to withstand strong winds. With the added risk of snowdrifts, we have to be mindful that this can lead to water ponding. For areas where heavy snow load can be expected, structures are generally designed to have smaller spans and a greater degree of inclination to encourage the snow to slide off. When designed appropriately, fabric structures can withstand the most extreme weather conditions. Manufacture. Unlike traditional construction materials such as brick and concrete, one feature of tensile fabric structures is that it can be entirely manufactured off-site. Large clear span spaces are required for the fabrication of tensile structures, as the surface area of a single piece can reach hundreds of square meters, although we are usually limited by the weight of large membranes more than the size.
At the point of design, we go through computer modelling, analysis with form finding, patterning of the material. After patterning, the basic fabric form shape is taken to the cutter plotter, which is behind me, is cut and then welded together.
Using such a wide range of fabrics, it is necessary to adopt a variety of manufacturing methods to cut and join tensile fabrics. These range from advanced sail-making techniques to more industrial large-scale manufacturing processes. Welding works for the majority of our fabrics and is suitable for external use. Some fabrics are joined by radiofrequency welding. This consists of heating the thermoplastic element in the fabric coating using electromagnetic waves to soften them and bond the two layers together. Advanced welding technology allows us to create an even strength across the length of the weld and a bond which will withstand extremely high tensile loads. Not all fabrics can be welded easily, and some require an additional layer of bonding tape to ensure the weld can achieve the strength and stability requirements for this type of application. The seam is designed to have the same tensile strength as the fabric itself. Sewing is suitable for smaller projects, and for reinforcement patches on some larger membranes, we use industrial sewing machines and UV-stable thread to join the fabric layers to one another. For some applications and some types of fabric membrane, including silicone-coated glass cloth, welding or sewing are not an effective means of joining. Gluing using a high bond adhesive will provide a joint with adequate strength and durability. Installation.
A conventional building construction means that the builder arrives on site, builds his foundations and builds the building up. Our industry is not like that at all. We fabricate most of the components off-site. So in other words, we bring to site in kit form the building and assemble on site. The biggest advantage of that is that we are not getting in anybody's road during the construction phase, and it means our time on site is relatively short.
As the majority of manufacture occurs off-site, the installation of a tensile fabric structure is fast in comparison to other building materials. Designing and manufacturing tensile structures which are practical for erection is essential. Therefore, components, connections, tolerances, weight and sizes are all considered from the early stage.
The majority of an ALA project is actually off-site, not on-site, and as such, the design and manufacture are critical to a successful installation. On the design side, we need to consider not only the architectural requirements, but also we need to look at the installation method and consider how this is going to be achieved.
Installation of a tensile membrane requires an understanding of the material and its behaviour. During the design and fabrication process, the membrane is tested and patterns adjusted to compensate for the inherent stretch in the fabric. When first delivered to the site, the membrane is smaller than required and only takes its intended size and form once tensioned into place using one of the many erection methods we can adopt. The skill and coordination of site operations are critical to the success of a project. Technical knowledge and experience of the construction and installation process often involves potentially high-risk operations with demanding access requirements or complex lifting operations.
There's two main skills that are required from site crews: is safety and also competence in the work that's being carried out. Safety is paramount. All our installers are qualified rope access technicians. They all got extensive experience in the use of mobile plant and working at height. The other requirement is that they're competent in the installation of fabric. Various different fabrics handled in different ways. PVC, PTFE and ETFE are all handled in different ways.
Depending on the type of canopy or structure being installed, installation methods can vary. Some structures have masts which are hydraulically jacked up or extended with a telescopic section in order to tension the membrane and support the structure. Smaller structures can have corners pulled out with rigging screws, U-bolts, or by shortening the perimeter mast to tie back cables. Individual scallops can also be tensioned by shortening the edge cable where it connects to the membrane plate. A very common method is to pull panels into parallel luff tracks and tension by drawing out the corner plates that slides inside the luff track. Conclusion.
Tensile architecture has been fairly futuristic since its inception, using materials such as PTFE, which was originally engineered for NASA and the space industry. One of the great things about working in an industry like this is you can never fail to be inspired by the weird and wonderful designs and ideas that people come to you with. There's nothing we like more than a challenge to take something that looks impossible and make it possible.
Fabric is now more incorporated into architecture. We are asked to make fabric work in ever difficult circumstances. That's part of the attraction, that we have to have the ability to make sure that we do end up with a finished structure that is exactly what we hope it'll be and what the client expects. That's the job we do here, to make the dream come true.
As for the future, fabrics are changing, the methods that we install, manufacture and design are all changing. And as technology gets better, our job to a certain extent gets easier. But no doubt our clients will continue to make things more and more complicated, and we will revel in the challenge.
This presentation has covered the basics in what is, to a certain extent, a limitless and unbounded industry. The principles described apply to the majority of tensile fabric structures, but with so many possibilities, methods will differ from project to project and application to application. There is a wealth of information available to you in our technical library. We are always keen to discuss new and exciting projects, so please give us a call.